Guys survive the rain? Morning. All right, 3, 2, 1. Welcome, EE123, lecture 22. Woo! Happy Monday. Okay. I have a question. Anybody here from this classroom recently voice was heard on the radio? No? I don't know. I thought I recognized. Oh. Okay. So, any announcement, John?
Homework and lab is due today.
Homework and lab is due today. Ham radio exam is finally coming up on Wednesday. So all of you, I assume, registered who needs to take it? Yes? Very well. All of you assigned times and things, gotten back emails? Yes? Yeah. Great. Okay. And then next week is spring break. We'll make sure that you're pretty busy during spring break. Okay. So, last time we talked about optimal finite impulse response filters. I just want to go briefly on what we do when you have an infinite impulse response that you'd like to design. We're not going to go too deeply into this. I'm just going to tell you kind of what the ideas are. There's a lot of tools out there, and you're more than welcome to look in the book of how it's actually done if you're interested in the exact details. And then we're going to move into Chapter 5, which is the transform analysis of LTI systems. You'll see that's really relevant to what we've already been doing when we're talking about filter design. Now we're going to analyze systems through their Z and Fourier transform. And then, yes. And then pretty much after that, we have all the rest of the material is going to be kind of additional material, including two-dimensional Fourier transform. We'll talk a little bit about compressive sampling, and so a little bit more advanced topics that are not in the book. So this pretty much this last chapter kind of summarized the material that we're going to cover from the book, and the material. most of the majority of the material for the second midterm. The more advanced stuff will ask you concepts, but not something in details. Okay, so IIR design. Historically, if you wanted to make an infinite impulse response filters, there is a lot of work that's been done in the continuous time domain, okay, for designing analog infinite impulse response filters. And so the approach was, okay, I have these tools that allow me to approximate very well the frequency response given some criteria using various approximation functions. So how about we go and we take the continuous time results and translate them into discrete time. Now, if you want to directly do in discrete time, things are not as trivial as in continuous time because of the fact that once you have something discrete, then the frequency domain has this aliasing in it. Okay, it has to be periodic, which causes some issues if you want to do some analytical, if you want to come up with analytical functions to do this. So the nice thing about continuous time IIR designs is that they have these closed forms. They're really easy to use. Okay, it's really easy to use. That closed form, you just plug in what is the cutoff frequency and so on and so forth, and then you got yourself the representation for the filter. Now, with IIRs, it's really easy to control the magnitude of the design, but it's really hard to control actually the phase. Okay, if you look at all those analytic functions, it's not really easy to control it. This is one of the reasons that we've been looking at finite impulse response filters in a discrete time, because it's really easy to design whatever that you want, actually, the entire complex Fourier transform. If you look at the common types of IIRs, there's a Butterworth filter. It's monotonic, no ripple. It's just basically, it's a monotonic function. Chebyshev filters, there's type 1 that has a bandpass filter, and type 2 has a stop band ripple. And then in the other part, they're monotonic. And then there's the elliptic filter, which has ripple in both pass band and stop band. And when you talk about ripple, that means that it has zeros, effectively in the Laplace transform. But also, if you then translate it to digital filters, it's going to have zeros in the Z transform. Okay, so those effectively cause the ripple. Okay. So how do you actually do this? Let's say you know how to design a analog filter, so analog frequency response. How would you then go about and translate those results into discrete time? Sampling. Right, so let's say you know the impulse response. Is that right? So you know the impulse response of the analog signal. Then yes, you can. What you could do is just discretize it. Okay, so yes, absolutely sampling. And one of the methods that people are using is what's called impulse invariance, where you want to match the impulse of the impulse response of the continuous time in the discrete time. Now, one of the things that you have to guarantee when you want to discretize is that, first of all, the imaginary axis of the Laplace transform need to be mapped onto the unit circle. And so whatever on the left-hand side of the complex plane needs to go inside the unit circle. And that guarantees that any stability in the Laplace transform would result in a stable discrete time filter. Now, the other approach is actually using what's called a transformation or a bilinear transformation. So you take the complex plane, and then basically you create a mapping which maps the left-hand side of the plane inside the unit circle and the right-hand side of the plane to outside of the unit circle. Okay? So this is called bilinear transformation. Now, if you look at Python, there's a lot of tools that you can use. These are part of the SciP package, in particular the single one. It's called IIR Design, and it encompasses all these Butterworth, Chebyshev, elliptic filters, and what's not in there. MATLAB has its own functions as well, and there's some equivalency between these and MATLAB's. Now, briefly, if you want to match the impulse response, what you need to do effectively is sample it. If you sample it, then what you'll get in the frequency domain is, of course, aliasing if the Fourier transform of your filter is not band limited. So you get deviations from the original transform, the original filter. Okay, that's basically what it means. And so that's one way that you could do it. The other way that people do is a transformation. So using basically what you do is you warp HC j omega such that it becomes band limited. Okay. If it goes from minus infinity to infinity, you map the range of minus infinity to infinity onto something periodic. And one of the transformation that it's used is called a bilinear transformation. Have you seen a Smith chart before? People have seen a Smith chart? This is a flipped Smith chart. And the reason I flipped it, because this is the result of how a grid in the S-plane would transform into a grid in the Z transform, okay, after this bilinear transformation. Okay. Have you seen us? Anybody took 117? 117? So remember, classes that end with a 7, good classes. Okay? 127 and 117. Okay? I recommend 117 for those interested in electromagnetics. This is, while very challenging, it's one of the most amazing things that exists out there. Okay. So this transformation basically tells you that you map the complex plane of the Laplace transform onto Z. And what you see that it satisfies that the left-hand side of the plane will be mapped into the unit circle, inside the unit circle. Now, what you need to do then, if you think about this, you can't map something that's rectangular and infinite into something that's finite and circle, right? Like the mapping is going to be like distorting. Like you have to distort things in order to do this. And so if you have a filter that specifies a certain frequencies over here, when you do the transformation, that's going to move those around. It's going to distort your passband. It's going to distort your stop band. And so what people have done then is, well, okay, so we know what is going to be the distortion, so we're going to prescribe a particular filter that's pre-distorted, that once we then map onto the Z-plane, then it will give us the right stop, the right filter specifications. Okay, the right stop band, the right pass band. Okay, so this is really how these filter design approaches actually work. Okay, now the problem is, of course, is that it is distorted. So yes, if you are okay with, if you want to design something that's a little bit more complex than just a low-pass filter, then yes, you have to kind of work in order to figure out how to pre-distort it correctly, okay, and how the phase is going to be affected, and so on and so forth. So it's not as trivial as you might think. If you look at the S-plane, this is just a simulation of how the mapping works. If this is the S-plane, and this part will be the stable part, and this one will explode, so the unstable part, this is how it maps after performing the transformation. You see it reads stable. Okay? But you see how it is distorted, but it is maintained inside the unit circle. And this is the explode part. So let's see. Explode. Yeah. Great. And you can see also how this grid here is mapped onto the grid over here. Now, one thing that you could see is the reason that these lines become thicker is because of interpolating those. Of course, the space stretches here significantly, and so when I computed this and I performed an interpolation, that's why they look wide. But of course, there shouldn't be. Yeah. This is not a point. This is a continuous time, right? Yeah. Yeah, actually, there is a one-to-one mapping. But the stretches, right? So whatever, for example, if you look at this line, it's really just a stretch version of this. So like in order to map here, you have to, this has to be made out of rubber, right? So the density is not maintained, okay? Obviously, because you take some infinite region and put it inside a finite region. Note that this part is missing, and this part is missing because really there's different parts of here that are not represented. Okay, this is also a crop through the S-plane, so that part is missing, and of course the outside of that too. Okay, so this is the basic idea behind designing IIRs. Now, when you look at IIRs, or in fact, when we represent them, we often represent them as a linear difference equation. So you have some coefficients for pass values of whatever output you have. So it's a linear combination of pass outputs and plus a linear combination of inputs or recent inputs to your system. Those have a very particular linear difference equation have a very particular form in the Z-transform. They're basically kind of represented as a fraction between a fraction of two polynomials. So you have the numerator and the denominator. Each one of them will be basically polynomials of the Z-transform. When you compute the Z-transform of what is actually the output of Y, the output of Y would be the Z-transform of this, and then so anything here will be a multiplication. So you'll see, coefficients here of B, and then divided by coefficients of A. And these are just polynomials in the Z-transform. Okay? So all the sum will be some polynomial Z. This will be polynomial in Z. And then you take this polynomial derived by this polynomial, and then you get this representation. Now, if you think about this, well, okay, what if I want to design the IIR filter directly? What would I do? And here's just an idea. This is another way that you could be designing IIR filters. And this is, again, not in the book, but I wanted to show you because I think it's important to just think of different and a more modern way of designing filters, not just necessarily the classical ones. And so here's the idea. What about, we did the same approach in the FIR filter design, where we had some optimality criteria or some difference criteria that we'd like to minimize. How about we also impose it on the IIR? And in the IIR, we have these effectively two polynomials in the Z-transform that we would like to design. One are coefficients of X, and one are the coefficients of Y, okay, of the outputs that we would like to design. Each one has a Fourier transform, and the result is really the Fourier transform of B divided by the Fourier transform of A. Okay, this effectively is the Fourier transform of, this is the frequency response of our filter. And we would like that to be as close to a desired response in the same way. And we'd like to do this matching over a certain region that we care about in some measure. For example, a square least or a minimum square error measure. Okay, this is one of the options. So the problem of trying to optimize this is that it's actually quite difficult. This is highly nonlinear, non-convex type of a problem because you have coefficients that you'd like to solve up here divided by coefficients you would like to solve. Okay? So that is an issue, okay, in order to solve this. So what people do is instead is approximate this as a weighted linear least squares. So before we had a linear least square problem where we wanted to design just an FIR filter. Here we can transform this problem by effectively saying, okay, so if we want to minimize this, how about we just multiply, just get rid of this. I mean, this is really annoying, right? This is really annoying. So how about we multiply both of these by a e to j omega? We'll get rid of the denominator. This makes it into a weighted least square problem, right? That is weighted by whatever a e j omega is. If you think about it, if I multiply by that, then it's the same as putting a w up front. So what we could do is say, okay, how can we represent this exact problem in a slightly different way? What we could do is say, okay, we want to solve effectively b e to j omega minus hd e to j omega times a e to j omega. And then multiply all this, weight that by some w of omega. And if w of omega is actually 1 over a j omega, which we want to solve for, it's a chicken and egg problem, then that would be the right problem to solve. Okay? But we don't know what it is, so I'm a little bit cheating here. But if I solve this, and I can prescribe a w that sets that, then I solve the original problem. And so what people do is they say, okay, well, we can't do this. So how about we start with 1, or maybe with some approximation of what we think A would be, and then solve the least square problem. Now it becomes a least square problem. Then we get the result, and then we use that to reweight W by A, and so on and so forth. And so this is one way that this is being optimized. Of course, it doesn't necessarily guarantee that you're going to get the optimal result of the original problem, because now you're relaxing it. But this is actually a pretty good approach. So what you do in order to do this, you discretize this problem and solve it. But of course, there's other issues that you can think of. How about stability? How can you guarantee that if you look at the roots of A of z, how can you guarantee that they're inside the unit circle, and so that filter would be stable if it's causal? Okay, you need to come up with an approach that would make that true. The other thing is that prescribing HD is also quite difficult. You need to prescribe not the real part of HD, or it's not the magnitude of HD. You actually need to prescribe the complex one, and the complex one that's actually feasible. If you just prescribe a zero phase one, then you're going to get a non-state, not necessarily a stable, causal solution, right? And it's more complicated. It's, FIR, you just shift it, but IIR is not as trivial because it has an infinite impulse response. So we can't just shift it. Okay, if you crop it, then it's no longer an IIR. Okay, so all of these issues, you have to come up with the right phase. Then that would result in something that is stable. And so people have done work in doing this, and it is possible to design what's called a minimum phase IIR filter. And we'll get to what minimum phase is when we, in a couple more lectures. It is possible to solve it through optimization, and you can actually get optimal results of this particular problem. Okay, not this particular problem. You can also try to solve this, but again, this is quite more difficult. Okay? So there are tools that you can do in order to design much better, more flexible IR filters with modern optimization techniques. So I just want you to know about this, because when, let's say, you get a job and you have to design IIR, and you want to design IIR that's a little bit more complex than what you have right now, then I would recommend that you go and you explore this other approaches as opposed to necessarily using the trivial. Okay, any questions before we move on? Well, they're absolutely, when they're not implementable. They are implementable. No. So these are represented as recursive filters, right? So they are implementable, and they are actually very efficient. And the truth is, in fact, when you have a recursive filter, you basically save a lot of computation. You don't have to go and compute what you already computed. So this is why people use IAR, because you can get, with less computation, you can get sharper transitions, for example. It's not as of an issue today with computation, but if you have a system that is limited by computation, then IAR might be actually your solution if you don't care about nonlinear phase. Okay? And we'll get to what even nonlinear phase means. If you don't care about it so much, then you might as well use an IAR. Okay, so they are absolutely used in the systems. They're not as often needed as they used to be. Especially today, if you're going to use a large FIR filter with overlap and add FFTs. I mean, yes, it's more computationally intensive, but we're talking about, okay, so you'll get to solve it in, I don't know, like a few microseconds, maybe a couple of microseconds more. I don't know. It really depends on your computing platform. If you're doing it on a Raspberry Pi 1, then maybe computation is an issue. On a phone, maybe computation is an issue. Okay, but otherwise, not necessarily. Okay, so now we're going to talk about these linear difference equations, and we're going to look at effectively what is a magnitude response and what is a phase response of these systems, and try to kind of get an intuition and understanding of how these relate to the Z-transform. If you have a particular Z-transform, what will be then the magnitude response and the frequency response of these systems? That will lead us, yes? Because we don't know what it is. We want to solve for it. If W would have been equal to AEJ omega, then that problem would be equivalent to this one. The problem is that we don't know what it is. So we start with some approximation, we solve this problem, and then we use the result of A in order to construct a new W and then resolve the problem, and then solve it again, and then use that result in order to resolve the problem again till we get some convergence. Okay? Okay. So once we talked about all these zero poles, how they affect the phase, then we're going to move into all-pass systems and linear phase, minimum phase systems and talk about them and see what nice properties they have and what type of structures they have so that we can use them in order to design systems and filters. Okay, what is the magnitude response? The magnitude response of a difference equation, linear difference equation, is prescribed effectively if you know how to write down the frequency response. The frequency response is really a multiplication of two polynomials. Let me just go back. If you have a linear difference equation, its Z-transform is just two polynomials, one in the numerator, one in the denominator. One is the polynomials of the coefficients of x, one is a polynomial of the coefficients of y. And so if you factor that polynomial to the roots, you can write it as a product of all its roots. Okay, both of the numerator one and both of the denominator one. We use C's in order to, or C sub k, in order to describe zeros of that function. They're called zeros because once a z equals to this value, then the entire function becomes a zero. Because this becomes a zero, then hence everything becomes a zero. And if decays, we call them poles because once z is equal to this value, then the whole function explodes. because you're going to be dividing by 0. Okay? So the roots of these polynomials, you can actually write them as factors of them. Now, effectively, what is filter design? Filter design is designing coefficients of polynomials. Polynomials of the Z transform. Polynomials in Z. These are also coefficients of the impulse response too. Okay, if we just talk in an FIR filter, then it will be just coefficients of the impulse response. On an IR filter, it's a little bit more complicated, but effectively is the coefficients of our recursion. Okay? Coefficients that sum all your, are the linear combination of your outputs. Okay? So when I'm going to say polynomial design, impulse response design, coefficient design, they're all kind of equivalent. So if you have this form of a frequency response, if I'd like to look at what is the magnitude of response, well, as it turns out, the magnitude response then can be described as the magnitude of whatever gain you have for that system, which is B0 divided by A0. Those are the zeroth coefficients. And then the magnitude of all these products, both in the numerator and the denumerator. And if you just consider a single pole, by the way, these drawings are from Murat Archak. When I took over the class, I took it from him, and he has this beautiful handwriting, gorgeous sketches. I had to keep some of his, legacy, and not convert everything to just keynotes. And I was lazy too, but it was just so pretty. Look at the I and the M, and it's just gorgeous. Okay, so let's just consider the case of one pole. Okay, if you have one pole, the pole is actually at dk. Okay, so 1 minus dk E minus j omega. We want to look at the magnitude of that. Okay, if I know the magnitude of that, then I can find what is the magnitude. If I have only one pole, then it will be h e j omega will be 1 over the magnitude of this. Okay, so I want to see what the magnitude of that. If I want to write what the magnitude of this, then I can pretty easily see that it's the same as the magnitude of E plus j omega minus dk. The reason is I can multiply by E the minus j omega and E minus j omega on both sides. They have a magnitude of 1, so it doesn't matter. It doesn't change the magnitude. If I multiply by the whole thing with E minus j omega, E plus j omega, then I've got this minus this. And the magnitude of this, it's a vector which I call V1. And let's look what actually it is. dk is a coordinate that where the pole is. E plus j omega is somewhere on the unit circle, which I want to evaluate what is the frequency response. What is the magnitude frequency response? And so I look at the difference between this coordinate and this coordinate, which gives me a vector V1, and I'm going to look at its magnitude. So effectively, the magnitude frequency response of a single pole system, is determined by the length of the vector from the pole to the unit circle, and it's going to be inversely proportional to it. Okay, if I want to actually look what the magnitude is going to be, it's going to be 1 over V1. 1 over the magnitude of V1. If that's a pole. If that's a 0, it's just going to be V1. Okay? So poles that are going to be closer to the unit circle, the V1, the vector is going to be smaller, hence I'm going to get more gain. If the poles are going to be further away, going to be less gain. If I'm going to get a 0, I'm going to get less gain when it's close and less attenuation when it's further away. Okay? So here's just an example of hz equals 0.05, 1 plus z minus 1 divided by 1 minus 0.9 z. We have a 0 at z equals minus 1, and we have a pole at z equals 0.1 on the reals. And so all I need to do in order to find the frequency, the magnitude of the frequency response, is to look at the vector what is the distance between the point on the unit circle, which I want to find what its magnitude is, to the pole, the one from the 0, and then I compute the magnitude of V2 divided by the magnitude of V1. And you can see that when you're close here, the effect of the 0 is diminished, and the effect of the pole is significant. And so as I move away, then V1 grows, and V2 shrinks, and then at some point when I reach this point over here, then the whole function becomes 0 because V2 is going to be 0. Okay, so I have a frequency response which looks like this, which is in fact a low-pass filter. That's right. This is a low-pass filter. It passes high frequencies and attenuates low frequencies. You can also see that from the frequency response, where this is attenuated and this is amplified. Okay. If you actually look at the low-pass filter, we can parameterize like a simple low-pass filter. We can just parameterize by 1 minus alpha over 2, 1 plus z minus 1 divided by 1 minus alpha z minus 1. So effectively, you have a parameter just determined by alpha, and if you want to set, and that guarantees, by the way, this guarantees the way that you put the gain here. It guarantees that the gain at DC would be 1. And then if you want to translate alpha into, you want to translate a cutoff frequency, which is minus 3 dB cutoff, into the parameter alpha, you just prescribe 1 minus sine omega sub c divided by cosine omega sub c, and that will actually guarantee that the cutoff frequency is going to happen at omega sub c. Okay? That's the point of 3 dB, because if you actually prescribe an alpha that way, then you see that at that omega, you get half. Okay? Sorry, 1 over square root of 2, not a half. Okay, so this is just a parameterization. Now you see that just because we looked at what is the frequency magnitude frequency response, that makes it easy to parameterize it that way, and then prescribe a very, very simple single pole, single zero filter. If you want to then parameterize a high pass, you can do it the same way, but now you just have to flip the I think just the sign, like you do a 1 plus alpha here, and then what's the difference? Yeah, just flip this, 1 plus alpha. Does that solve it? Is that correct? I don't think so either. But no, you have to change the sign. I think I need to change the sign of this one. Okay, I'll take a look and I'll fix those. But effectively, it's pretty trivial to you need to you need to flip the sign. So this has to be a minus here, and this has to be a plus here. Basically, that flips the zeros and the poles from their position. One is go the other way and one the other way. Yeah, so this needs to be flipped. Okay. Then you can also so if you want to look then at a system which is a simple band stop or a notch filter, a band stop or a notch filter has this particular form. But if you actually stare at what would be the zero and pole diagram, then you've got zeros that notch a particular frequency. You want to put the zeros exactly on the unit circle. And then in order to compensate for the magnitude, you want to put the poles as close as possible or close to the zeros in order to cancel their effect on the long term. If you think about this, if you have a pole and a zero over here, And if you look at the magnitude far away from them, then the effect kind of cancels. Okay, kind of cancels. And so if you parameterize this in this particular way, then you see that the frequency response of this bandstop filter again can be parameterized by a beta and an alpha parameter. And once you prescribe, if you look at what alpha is, as alpha gets larger, alpha basically means where the pole is going to be. How close is it going to be to the unit circle? As alpha gets larger, up to the value almost 1, then you get a more narrow and narrow response. Effectively, when alpha, if those would be exactly the same place, then the 0 would cancel the pole, and then you're not going to get cancellation anymore. They become narrow, too narrow in that sense, right? Infinitely narrow. And then if you want to control what is the frequency response, just a second. If you want to control where is the notch is being done, then you basically prescribe beta to be cosine of omega 0. Yes.
Your poles have to be outside the angle.
No, it's just next. It's like closer. Yeah.
Okay, and then how do you set it so that you get 1 as your frequency response magnitude at DC?
Pardon?
Like a formula for that?
Yeah. So this is basically how the gain is set, so you get the magnitude response to DC. And then you can see that this is actually true because if you look at what was my point was? Yes. So if you look at the bandpass filter at plus minus 1, effectively, as alpha goes to 1, then the poles basically approach the zeros, get as close as possible to the zeros. So if you look at what actually happens, it's alpha approaches 1. When this approaches 1, this approaches 2, this approaches 2, and then you've got yourself a magnitude of 1. Okay, so at plus minus 1, then you'll get a magnitude 1. You can also look at a simple bandpass filter. If you parameterize in this particular way, if you have, again, it's a second order system. If you look at how to parameterize it's parameterized in the same way, where now omega 0 is the inverse cosine of beta. And again, the larger alpha would reduce the passband, longer alpha would, smaller alpha would reduce. So again, you have got now zeros that hold pi and that hold the frequency 0 and pi to zeros, and then you've got yourself poles that amplify your magnitude response at a particular frequency. Yeah. No, okay. So when you have a system of 2 zeros, 2 poles, then it has that kind of a Fourier transform. That is the form of the z transform of the transfer function. That just comes from the fact that you have a 2-order second-order polynomial at the bottom and a second-order polynomial at the top, and then we just normalize it by this parameter such that the magnitude at the frequency of interest would be 1. Okay, so this is just a normalization. Yeah, pretty much. But this is a specific parameterization that allows you to come up with some very simple filter characterization. So you want a certain width, then or in particular for the case of a low-pass filter, if you want to design a certain cutoff frequency, you immediately know what is the value that you need to put for that system in order to achieve that. Okay. These are just examples of looking at the magnitude response. We completely, though, ignored the phase response at all. And so the next thing I want to look is what's the effect when you have zeros and poles on the phase. And what does it actually means even a phase? What does it mean phase response? This is elusive. Like people don't get what a phase response is. They often just ignore it. Like usually you don't even plot it. Right? We just plot like in Baudet diagram. Like we just mostly plot the magnitude as if that's the most important thing. But that's actually not the case. If you look at a very simple system, which is just a delay system, okay? A delay system or a linear phase system, here's an example where h e to j omega is equal to e minus j omega times nd, where this is a integer. That would correspond to a delay in the time domain. Okay, a delay in the time domain. The magnitude of that system is 1. So that system really doesn't do anything to the magnitude response, but obviously it has significant effect on the time signal. It delays it. Okay, so things shift and move. Okay, so there's no attenuation of frequencies, but there's obviously stuff going on there. So the magnitude is 1. And if you look at the argument, or what is really the phase, and the terminology we're going to use is when I use small letters, then this is really the unwrapped phase. And when I use capital letters, is the wrapped phase, because phase is only defined between minus pi and pi. But that function, omega n sub d, is actually a continuous function. I can prescribe omega to be, whatever value I want. Okay. So if you look actually what is the phase here, the unwrapped phase, it is a linear function. It's a linear function of frequency with a coefficient that is the delay. So a linear phase in the frequency domain, when the phase is a linear function, that will correspond to a delay. If the slope is negative, the delay is, things are delayed in time. If the slope is positive, then things are advanced in time. Okay? That's what it basically means. And so this is very interesting, because what I could do now is I can look at arbitrary phase filters, and from there I can try to kind of say, well, if linear phase is the delay, I can then try to analyze what is the delay of nonlinear phase filters. And how does it actually, what even does it mean? What it's going to mean is going to lead to what's called a group delay. Group delay is a way to characterize general phase responses. And so what the group delay is really the negative derivative of the phase response. Now, why is that even interesting? The reason it's interesting is if I had a phase response that is nonlinear, if I zoom in at a particular bandwidth, at a particular frequency, let's say I'm going to look at around the frequency omega sub 1. And I'm going to look there. By the Tyler approximation, I can approximate this as a linear function. I mean, as I go and I zoom in, it's going to look like a linear function. And what does it mean then, a linear function? It's going to look like a linear phase for a narrow band pulse that's going to be around that frequency. So if I have a pulse that's narrow in bandwidth, for example, if you look at a short time Fourier transform kernel, right? It's a windowed, if you take a particular frequency and then you window it, that would be a narrow band pulse that has a particular bandwidth around omega sub 1. It's not going to see what's going on in omega 2. It's not going to see what's happening at omega 0 or any other frequencies. What it's really going to see is what is the behavior around omega sub 1. And what it's going to see is a phase that's approximately linear. So what's gonna happen to that particular pulse? It's going to be attenuated or amplified by the magnitude response, and it's going to be delayed by the group delay at this point. Because effectively the group delay tells you what is the derivative, what is the slope at this place. And if you look at the linear phase, the group delay here is just uniform. It's everywhere. It's exactly the same on all frequencies. Because it's a linear function. If you look at the derivative of a linear function, it's just a constant. But in this case, it's also a function of frequency. Hence, that pulse is going to be delayed by a certain amount. Another narrowband pulse around omega sub 2 is going to be delayed by a different amount. And hence, I'm going to get what's called a dispersion. That's what happens to light when it goes through a prism or a lens. Different frequencies, or for a lens, maybe different angles, are going to be delayed at a different differently. That's what happened on a fiber, optical fiber. Different frequencies are going to be delayed differently. They're not necessarily going to be attenuated, but it's going to distort your signal quite severely. So here's just an example. Let's say I have a group delay that looks like this, a filter with a group delay that looks like this. This is the input to that system, and this is the output of that system. Look what happened. Omega 2 says, yeah, you're not going to delay by much. This pretty much, you're going to stay almost the same place that you started with. The slope here is pretty much constant. Okay? Again, this is a drawing. It's not perfect, so don't get me. The idea here that the slope is not significant. And here the slope is more significant, so frequencies around omega 1 are going to be delayed significantly. And here's the result. You put a narrowband pulse around omega 1, followed by a pulse around omega 2, and then the result is going to be that the pulse around omega 1 is going to be delayed a little bit, but the pulse around omega 2 is going to be delayed significantly, and it's actually going to pass it in time. Okay? So this was the last to be transmitted, but it was the first to arrive. Cool, right? And what if you have now more complex signals like voice or, data? Then you get a mess. But here's the thing. If there was no attenuation, then if I would have prescribed the conjugate system that has the opposite delay, that has the opposite slopes, this would be delayed more and this would not be delayed as much, then I can actually correct and put them back into place. Maybe after a longer delay, but it is maybe possible to do. So if you have a pulse that you send and it starts spreading around, goes lower and lower and lower, and then out you put another system at the end, and then everything comes back again. Maybe that's possible. Maybe there's actually a good reason to do this. Let's say our voice fluctuates, right, over time. If I want to run it through an amplifier, it doesn't give it good efficiency. Right? I have to really change amplitude very, very quickly, over and over and over again. Right? Then I have to use a very linear amplifier that I have to meet this, and it's not really efficient from a power point of view. What if I run it through a system which spreads things around, this doesn't attenuate everything, but now I've got more continuous energy spread over time. So now my signal is spread. Distorted, right? Transmitted, then when I receive, I can correct for it. Hence, I solve myself some issues. Okay? All right. So what we're going to do next is we're going to look at, again, what would be the result of a single pole or a single zero on the phase response. We're going to look at those effects, and then we're going to move into describing what our all-pass systems linear phase systems and minimum phase systems, and also characterize those because these are subclasses of systems that are very important, and we use them all the time. With that, I think I leave the